we're going to be looking at how we're supporting the definition and navigation of complex network relationships using the new user-defined link capabilities we've added. Some common customer use cases for this would be our customers wanting to define the implicit relationships between both sides of network address translation, or they want to document how overlapping address space defined in two or more different address manager configurations is related. Another good example would be the definition of how an IPv4 network and an IPv6 network are related when using dual stack in a site. So let's now take a look at the architecture. How does this actually work? Firstly, new REST APIs have been created to define and manage the definition of a new navigation link type called the user-defined link. This defines the implicit relationship. Links can be added, retrieved, deleted, and updated using the new REST APIs. Once the user-defined link type has actually been defined, customers use new linked entities EX calls to link or unlink explicit entities defined in Address Manager by using their object IDs. These new calls should not be confused with the older linked entities calls, as they serve a very different purpose. Finally, the user-defined link definition will automatically be shown on the Details tab for infrastructure which has been linked, but it can also be added to most tables, as if adding the existing UDF to the view in question. We're going to be using Postman as an API client, making BAM REST API calls to Integrity 9.3. We'll also be looking at how the user-defined links themselves appear in Address Manager and how they can be used for navigation. In Demo 1, we're going to be looking at one of the use cases already mentioned in the architecture section. That is, we're going to be creating a user-defined link definition for the dual stack use case. Our JSON descriptor of the link type will define an implicit relationship between IPv4 networks and addresses to IPv6 networks and addresses, and we'll call the add user-defined link API passing the name dual stack. We'll then be linking our explicit IPv4 networks and addresses to IPv6 networks and addresses using this new dual stack UDL type, but passing this time the linked entities EX calls. And finally, we'll look at navigating them in the graphical user interface. As we're using BAM APIs, the first action in Postman is to get a login token, which we'll be using as an environment variable for the rest of our calls. Now we have a token, we'll be defining our new UDL to describe that there is a relationship between IPv4 and IPv6 infrastructure. We'll start by performing a post to the add user-defined link API, passing in some link definition JSON. We'll call the link type dual stack, and we're also going to set the same display name to be used in Address Manager. We'll need to set our source entity types to IPv4 network and IPv4 address, and the destination types to IPv6 network and IPv6 address. Upon sending our post, we receive a 200 OK response, indicating the call was successful in adding the user-defined link for dual stack. Now that we have a user-defined link dual stack created, we need to explicitly define the infrastructure connected under this link. We're going to be using a put call to linked entities EX and passing entities link JSON, saying to use the dual stack link type, but also passing the object ID of an IPv4 network. In this case, we're going to be linking 172.17.44.024, and the destination object ID is an IPv6 network, 2000/64. Once the API call is sent, we'll receive a 200 OK response that the relationship between networks has been made. Our dual stack user-defined link also defined that IP addresses can be linked between IPv4 and IPv6. So we'll be making a second call to the linked entities EX, but this time we'll be explicitly linking the IPv4 address 172.17.44.10 using its object ID to an IPv6 address 2000::1, again using the object ID as the destination. Again, upon sending this, we'll receive a 200 OK response back that the second relationship between the IP addresses has been correctly made. If we now take a look in Address Manager and browse to the network 172.17.44 details pane, we can immediately see that the user-defined link dual stack is automatically shown. We can also now easily navigate back and forth between our explicit IPv4 network and IPv6 network with ease. If we now navigate to the IP addresses table for the network and take a look at the details pane for an IPv4 object on the .10 address, we can already see that the user-defined link type of dual stack is presented there too automatically, just as it was for the network. But in order to make navigation easier from the table view for users, it's also possible to add the UDL as a column shown in the existing table. We can do this in exactly the same way as adding a user-defined field worked in prior releases of Integrity. By selecting the Customize Table option, we can see in the left pane that our user-defined link for dual stack is now available. We can add the UDL to the table and adjust the ordering just as we can for user-defined fields. Once we apply this action, a new column called dual stack is present on the table, which again will allow for the quick visibility that there is a link present, but also navigation to the destination IPv6 address and then back from the IPv6 address to the IPv4 address. A quick recap on what we've seen in Demo 1. We've shown how to define a new implicit relationship between IPv4 networks and addresses to IPv6 networks and addresses, and we've called this dual stack. We've defined the explicit infrastructure using this UDL using the linked entities EX call, and how this relationship can now be navigated in the address manager. This demonstration of user-defined links showed how a customer could meet their need to document the relationships present in dual stack network environments. In Demo 2, we're going to be creating a UDL to document and navigate network address translation in the address manager. We'll be creating a new JSON link definition which maps between IPv4 networks and addresses to other IPv4 networks and addresses. But this time we're going to be using configurations too, as we'll have overlapping address space. We shall start by creating a simple static NAT between two individual IP addresses. Then we'll follow up with another example using many addresses, in this case RFC19 network in a separate address manager configuration, mapping back to a single public IP address in our default configuration. This will document the NAT you're probably using at home, where your home network is on RFC19 space, linked to a public IP address owned by an internet service provider. Again, we'll be defining our link JSON, creating it with the add user defined link, and then we'll move on to linking the infrastructure explicitly using linked entities EX calls. Finally, we'll take a look at the address manager again to see how this user defined link relationship allows for navigation. So in Demo 2, we'll start by adding a new user-defined link called NAT. In this definition, we're going to be linking IPv4 networks, addresses and ranges to other IPv4 networks, addresses and ranges. This will allow us to model some common NATs, such as a static NAT between two IP addresses, but also a NAT where a single public IP address is mapped to a network in a different configuration. We've now received a 200 OK back from the API, indicating that our NAT definition has now been added to the system. We'll now start by adding a static NAT between two IP addresses. So we'll need to make another call to link entities EX between both sides of this relationship. In this use case, we'll be linking a public IP address on 172.17.44.10 using its object ID to a private IP address 192.168.1.10. But in this example, the IP address on the other side is in a completely different network and configuration. A 200 OK response indicates this link under the UDL NAT was successful. We'll also create another linkage using linked entities EX calls, but this time it's between a single public IP address on 172.17.44.11 to an RFC19 network 192.168.10.24, which exists again in another configuration. This time it's for our UK office. As there can be lots of RFC space in a customer environment, we're showing how UDLs can be used to document and navigate lots of overlapping address space. Now we can see that our 172.17.44.10 address in our default configuration has a one-to-one static NAT relationship to 192.168.1.10 address in the configuration VRF02. Clicking on this relationship now automatically will take us to the private IP address in the different configuration. And if we navigate back to our public IP address, we'll land on the details pane, which will show us something else. We can see this IP address has two UDL links which can be followed. This is as we've added our NAT relationship to the IP address we used in Demo 1, which also has a dual stack UDL. Taking a look at the IP address on .11, we can again see this is part of our NAT relationship. But in this instance, the IP address maps to a different configuration again, this time on the network 192.168.1.10 in our UK office. We can then navigate to this destination network in a different configuration with ease and then navigate back to the source IP address. Recapping what we've just seen in demonstration 2, we've shown how to define a UDL for a network address translation relationship, how to link entities together to form different NAT types, and how this can be navigated between in the address manager. But this time we use different configurations, as destinations of NATs may require overlapping address space. In Demo 3, we're going to be creating a new UDL for VRFs, e.g. virtual router functions, where the destination address block will reside in different address manager configurations. This is because VRFs may be overlapping address space, and we'll be mapping this back to the device type as a source entity. This will allow the user to see on their router devices which address blocks in different configurations make up the relationship and also navigate between them. We will, like the prior demos, create a new JSON link description, this time called VRF, which links devices to IP4 blocks. We'll initialize the link type using the Add User Defined Link API, and then link our device to the IPv4 blocks in different configurations. Finally, we'll take a look at this relationship in the Address Manager. As per Demo 1 and 2, we'll start by adding a new UDL type to represent our VRF relationships. This time our link definition is going to utilize the device type as a source and an IPv4 block as the destination. Add User Defined Link is used with our JSON link type description, and a 200 OK response indicates that the link was successfully defined in integrity. Linked entities EX calls are now being used to create one-to-one relationships between our Cisco ISR device in the default configuration and overlapping blocks in other configurations. We've actually named the configurations as per their VRF labels. We'll start by linking our Cisco device to an address block 172.17.00.16 created in our VRF01 configuration for the UK office. This is an overlapping address space, so we already have that block in our default configuration. We're then going to move on to linking our Cisco device to address block 10.00/24 created in VRF02, our Cisco device to an address block 172.16.00.20 created in VRF02, and finally we'll be linking our Cisco device to an address block 192.168.10.24 created in the VRF2 configuration as well. Our device is now being linked to two different configurations, each representing a different VRF label, each with overlapping address space in the RFC19 ranges. This could be representative of a customer acquiring other companies where address space for the acquired company overlaps with address space already used by the parent organisation. Upon returning to Address Manager, we can now go to the Devices tab to see how our Cisco device is now linked to overlapping address blocks in different Address Manager configurations representing our VRF labels. The VRF UDL can be navigated either by hovering over the VRF UDL on the device's table view or in the automatically created pivot table on the device's details pane. We can now navigate between the device and its VRFs and of course overlapping address blocks. This implicit relationship between VRFs is now documented and navigatable in integrity. Another variation of this link type could be utilised with Cloud Discovery to allow for navigation between a default configuration and any overlapping configuration added by CD&V for a VPC or VNet. A quick recap on Demo 3. We've shown how we can document VRFs by utilising a link type definition between a device and an IPv4 block. VRFs may have overlapping address space defined, so we've used different configurations which represent the VRF labels. We've linked all of our explicit infrastructure under the new UDL and shown how we can navigate this new implicit relationship now present on our device from the Address Manager. In our final Demo 4, we're going to take a look at the life cycle of a user-defined link. We're going to start by getting the existing VRF link definition we created in Demo 3 using the Get User Defined Link API, and then all the entities that are currently linked together under this UDL using the Get Linked Entities EX API. We'll remove one of the existing links using the Unlinked Entities EX API and check the results in Address Manager. We'll then remove the remaining links and then call the Delete User Defined Link API to remove the VRF UDL definition completely. After doing this, we'll confirm in the Address Manager that the UDL definition has disappeared and the links are no longer present on our device. We're going to start Demo 4 by utilising the Get User Defined Link API and passing it a link type of VRF. This will retrieve the definition we created in Demo 3 to represent our device to IPv4 block definitions. We'll return the JSON representation of the VRF UDL, which can be used if required with the Update User Defined Link API to modify the relationship further. But in this demonstration, we're going to next utilise the Get Linked Entities EX API. We're calling the API and passing in the object ID and the link type of VRF. The object ID is our Cisco ISR device. The return from the API will actually show all of the object IDs for the IPv4 blocks we linked in the demo 3. The returned object IDs are the link destinations we can see here in Address Manager. We're going to continue demo 4 by removing a single link from a device. We'll make a call to the unlinked entities EX call, passing in the link type of VRF and the source and destination object IDs to remove the link between the Cisco ISR device and the block 172.17/16 in our VRF01 UK Office configuration. We can already see in the Address Manager that the link between the Cisco ISR device and the block has now been removed. We'll now make further calls to the Unlinked Entities EX API to remove the one-to-one relationships we defined in Demo 3. First, we're going to remove the link between the Cisco ISR device and the block 10.00/24 in VRF02. Now this has been removed, we'll also remove the link between the Cisco device and the block 172.16.00/20 in the VRF02 configuration. And now that's finally been actioned, we'll remove the final link between the device and the 192.168.10/24 block in the VRF02 configuration. With all the prior link relationships having been removed against the VRF UDL, it's now possible to completely remove the link definition itself. You cannot remove a link definition if there are any entity links utilising the definition present in the Address Manager. But as we've removed all of these, we can now make a call to the Delete User-Defined Link API to remove it completely. This action will remove the UDL VRF from the device details pane, and if the link was added to the columns in the devices table, then it will also disappear from the Address Manager. To recap what we've shown in the final Demo 4, we've shown how to complete a UDL lifecycle. Firstly, we use the APIs to get an existing UDL definition. We've shown via the APIs how to get the linked entities currently using a specific link definition too. We moved on to remove the one-to-one entity relationships using the unlink APIs and shown how this updates the Address Manager. Finally, we completely removed the UDL link definition itself.